So hello everyone, we will be starting with lecture number 23, alright, and we'll be starting with a new concept that is called as concept of admittance. Okay, please write along with me. You have heard about impedance, you have heard about resistance, you have heard about reactance, but we will be talking about admittance now. So what is admittance? Basically admittance, which is represented by notation Y, okay, is a reciprocal of impedance, is reciprocal of impedance, which is represented by Z. All right. So if I represent this, please write along with me. So if I represent Y bar, it will be 1 upon Z bar. All right. Now let's say Z bar. Normally, how do we represent Z bar? R plus minus J X. Whether it is XC, XL or XL minus XC, it depends. Whether here it is plus or minus, it depends upon the nature of the AC circuit. So I can write it over here, 1 divided by R plus minus JX. Alright. So we can write it in this form. Y bar is equal to 1 upon R plus minus JX. I'll multiply and divide by R minus plus JX divided by R minus plus JX. Okay, I've divided and multiplied by R minus plus JX. Alright. So the numerator becomes now, so Y bar will be R minus plus JX divided by R square plus X square. Okay. So this I can write it down as, I break it down into two steps. It will be R divided by R square plus X square minus plus J into X divided by R square plus X square. Are you getting it? So you have completed up till here? Yes or no? So that I can proceed. Have you noted down the steps? Hello? Okay. So we have represented y bar is R upon R square plus X square minus plus JX upon R square plus X square. Now this term over here is called as, this entire term is called as G, and this term over here is called as B. Okay. So now we'll write it further as, that is Y bar is equal to J G minus plus J B. It is represented in this form. Alright. What was the counterpart? Let me add the students. Please join via Sumaya email ID only. Okay. So Z bar is equal to, what was the format? R plus minus JX. And your Y bar is represented by G minus plus JB. Okay. So here let me write the various terms. What is Y bar? It is called as admittance. Admittance, and its unit is mho. Opposite of ohms, mho. Okay. G is called as conductance. Okay. So basically G is my real part. See, this is real part, G is real part, B is imaginary part. So it is the real part of Y bar. Alright. And next we have is B. B is called as susceptance. Okay. Its unit is also mho. This unit is also mho. Alright. And this is also the imaginary part of Y bar. Alright. What is G given by? Where we can write it down over here as G is called as conductance and B is called as susceptance, where we can write G is given by R upon R square plus X square, and B is given by X upon R square plus X square. So please write it down. This is very important. Okay, all the terms are new to you. Please note it down. Completed up till here? Alright. Now, let's write for, so we have written point number 2, now point number 3. For RL circuit, remember, for RL circuits, what is Z given by? Anyone remembers? Z was given by R plus J XL. So counterpart, what will be Y given by? G minus JB. Okay, this is the counterpart in admittance. So similarly for RC series, RC circuit, what was Z given by? Z was given by R minus JXC. Correct? What will be Y given by? G plus JB. So please note it down. Completed? Up till here? Any doubts so far? Okay. Now we start with parallel AC circuit. I hope you have written up till now. Now we start with parallel AC circuits. So please note down this diagram. So let's say you have a parallel RC network. This is RC series and this is in parallel with RL series network. Okay, so these two circuits are connected in parallel elements. So this is my voltage supply, this is V and the unit is Hertz. Now my current in this parallel network splits up. So if this is the total circuit current I, it will be splitting up into I1 and I2. Remember, in a parallel circuit, current splits up. Alright. Now this branch over here, this I call it as R1 C1. Let me write it down. This is R1 C1. This is R2. We can write it as L1. Okay. So this branch over here, I'm calling it as Z1. So this is my branch number 1 and this is my branch number 2. So this branch I'm calling it as Z2. Alright. So what are the distinguished features of parallel circuit? In a parallel circuit, parallel AC circuit, voltage V is same across each branch. Voltage V is same across each branch. Current I is different in two branches. Okay, that is what we have written it as I1 comma I2. Alright, so where do we use parallel circuits? Parallel AC circuits are more often used in practice as all the lightning and power circuits and loads are connected in parallel. Okay, mostly in residential units where all the the connections are are light in load are connected in parallel. Now there are three methods of solving parallel AC circuits. So write down the three techniques. Three methods of solving or attempting parallel AC circuits. Okay, so the first technique over here is by phasor diagram. We will see shortly how to solve it by phasor diagram. By phasor diagram we can solve it. Second technique is by using phasor algebra. Phasor algebra. And the third technique is by admittance method. Okay, so these three techniques will be solving one by one. Okay, is it clear? So far you have reached up till here, yes or no? Hello. All right, now let us first tackle the phasor diagram. So let's start with phasor diagram. For the phasor diagram, now this phasor diagram technique will be valid or will be applicable only for two branches if there are two parallel AC branches. Okay, for AC parallel AC circuit, this is applicable for two branches like the circuit which we have shown earlier. It is applicable here. It is two branches only available, right? So this phasor diagram will be becoming complex if there are more than two branches. All right, so what we need to do over here is, let me just write it down. Okay, cancel it. A part is will find the magnitude and phase. Write this, please write it down. Will find the magnitude and phase of each branch current. All right. And the second part is you draw the phasor diagram. Draw phasor diagram taking voltage as a reference. Taking voltage as reference. So these are the two steps which we need to follow. So let us start with parallel AC circuits. I am redrawing the circuit for your reference again over here. So let me draw it over here. We have R1, C1, and then we have R2, L1. Okay, both of them are connected over here in parallel, and the AC voltage is V. All right. The current flowing through each branch, here it will be I1 and here it will be I2. This current is I. Okay, so far so clear? Yes or no? Now how do we start? You start by taking voltage as a reference. So this is my voltage. Okay, now can you tell me, in case of a RC series circuit, my equivalent current is leading or lagging the voltage? Can you all tell me? In case of a RC series circuit, can you tell me? Yes? Yeah, leading. Now tell me this example. Let us, draw the phasor diagram for this first. Let's say we have a pure capacitor and pure inductor connected in parallel to a AC circuit. Let's say like this. So you have capacitor and inductor, and the current flowing over here is, let's say, I1 and I2. Let's understand this first. This is voltage V. So if I want to plot the phasor diagram for this, let's say this is my voltage. Okay. Now how will I draw the phasor diagram for a pure capacitor? For a pure capacitor, the current is leading the voltage, right? So this will be I1. Is it true? This is true for pure C. And if the current flowing through L, the current is lagging the voltage by 90 degrees, right? So this will be here, I2. Correct? Have you understood this? This part which I have written over here, this is for your reference. Have you understood this? For a pure capacitor, current is leading the voltage by 90 degree. Here it is 90 degree. And for a pure inductor, current is lagging behind the voltage by 90 degree. Correct? But here it is RC and RL. So in case of a RC network, the current is leading the voltage, but not by 90, by an angle of phi, where phi is less than 90 degree. You remember, right? So over here, if I want to plot, my current will be leading the voltage but less than 90 degree. So this will be less than 90 degree. Did you understand? Yes or no? And this angle will be phi 1. Hello, are you all following? In reality, if it is a pure capacitor, it will lead by 90 degree. But since there is a resistor, it will be leading by angle phi, which is less than 90 degree, where phi 1 is less than 90 degree. Agree? Similarly, what will be L1? I mean R1, here it is R2, L1. For RL circuit, it will be lagging behind. For inductor, it will be lagging behind by 90 degree exact. But if it is a resistor connected, it will be lagging behind by a phase angle of phi 2, let's say. So here I will draw current I2, and this will be my phase angle phi 2, where phi 2 is also less than 90 degree. Okay, why not exactly 90 degree? Because R is present in series with it. Okay, have you understood? Hello? Okay, now I have to draw the equivalent current I, circuit current I. How will I do it? Can you all tell me? I have to draw the parallel over here, parallel to this. So this will be, I'm drawing it parallel over here like this, and parallel to this over here, this one. Okay, and the equivalent, the resultant will be over here. This will be the resultant. Let me draw the resultant carefully. You remember law of parallelograms? I'll draw a parallel line to this and draw a parallel line to this, and I draw whatever is the the result. I'll join them together. You have studied this somewhere, right? So this will be I. This current over here will be I. Okay, vector sum of I1 and I2. Got it? Okay, so please draw this diagram. And this angle is phi. This is the phase angle of the circuit. Okay, this is the phase angle of the parallel circuit. Parallel AC circuit. Alright, where you can write over here I is vector sum of I1 plus I2, where I is the line current, which is the phasor sum of I1 and I2, we can also call it. Okay, so what is the phase difference between V and I? Phi. So please note it down. This is my phasor diagram for parallel AC circuit. This is the parallel AC circuit given to you. Understood? Can I proceed from here? Hello? Okay. Now, tell me, here I will be writing over here, what is Z1? Z1 bar for this network. This is Z1 and this is Z2. So can you tell me what is Z1 bar? It is R1. Here it is RC. So it will be minus J XE1. Are you getting it? Similarly, what will be Z2? It will be R2 plus J. Here it is L1. So J XL1. Are you understanding how we have written this? Yes? Okay. So then Z1 square will be R1 square plus XE1 square, and Z2 square will be R2 square plus XL1 square. Got it? Now second part, what is current I1 given by? Can I write current I1 as V upon Z1? Yes. And current I2 as V upon Z2? Yes or no? Because basically your I1 into Z1 is V and I2 into Z2 is also V. Correct? Here I'll write it down. I1 into Z1 is voltage V and that is equal to I2 into Z2. So how will I write I1 as? Can I write I1 as V upon Z1? Yes. And similarly, I2 will be V upon Z2. Now, here, if I check phi 1, what is phi 1 now? Can you all tell me what is phi 1? If I take from here, tan inverse, can you all tell me what is phi 1? This is the magnitude. What will be the phase? Tan inverse of XC1 upon R1, and phi 2 will be tan inverse of XL1 upon R2. Are you getting it? Yes? Did you understand how we got phi 1 and phi 2? See, phi 1 we got it from here. I mean, over here. Okay? And phi 2 from here. This is the magnitude and this is the phase. Magnitude is R1 square plus XC1 square, and the phase will be tan inverse of XC1 upon R1. Okay? Up till here clear? Yes or no? Okay. This is the first method. It is only valid. This is the phasor diagram technique. It is applicable for two branches. So if you see a parallel circuit with two branches, you can apply this technique. Okay. So this is the magnitude. This is the magnitude. And this is the phase of each branch. Alright. Now let's go by the second technique. Second technique is phasor algebra. Okay. So write it down. Technique number 2. You solve by phasor algebra. Okay. So what do we do over here is, here voltage, current and impedances are expressed in rectangular or polar form. Okay. Here current, voltage and impedance are expressed in rectangular or polar form. Okay. So let us represent V first in polar form. So V bar will be given by V minus J0, and it will be this is in rectangular form. Polar form it will be V angle 0. Remember, this is the RMS value. Okay. What was Z1 given by? Z1 bar given by Z1 was R1 minus J XC1. We are talking about this circuit. We have RC. So this is R1 C1 and we have R2 L1. Okay. This is the circuit we are talking about. I have drawn it again. This was Z1 and this was Z2. This is V hertz. Okay, this is the parallel AC circuit we are talking about. So Z1 is R1 minus J XE1. Now how do I represent it in terms of polar coordinate? This is rectangular. Polar coordinates will be Z1 angle minus phi 1. We remember why minus, because the circuit nature is capacitive. And what is Z1 given by? Z1 square is R1 square plus XE1 square. And what was phi 1 given by? Anyone? Tan inverse of XE1 upon R1. Just now we have written it in the previous steps. Okay. Then Z2 bar will be R2 plus J XL1. So that I can edit as Z2 angle phi 2. Okay. Where what is Z2 square? Z2 square is R2 square plus XL1 square. And what is phi 2? Phi 2 is tan inverse of XL1 upon R2. Got it? Okay. Now similarly, what was I1 given by? V upon Z1 bar. Okay, what was I2 given by? V bar upon Z2 bar. So how can you divide two phasors? We can divide by if they are in polar coordinate. So that's why we have written the polar coordinates of everything. And finally, if you want to find the current, current will be I1 bar plus I2 bar. All right. Are you understand? Did you understand how to solve it by phasor algebra? Represents current, voltage, and impedances in rectangular and polar form or polar form. Okay, is this clear to you? Whatever is there in your screen, so that I can move ahead. Any doubts over here? Yes or no? Hello. Can I start with the next one? Okay. So the third technique we will start now. The third technique is by admittance method. Okay, by admittance method. So by admittance method, you remember what is admittance represented by Y, and it is 1 upon Z bar and represented as mho. We'll consider the same circuit. This is R1 C1. So this is R1 C1. This is R2 L1. They are connected in parallel. R1 C1 series is connected in parallel to R2 L1, again series. So two series network are connected in parallel over here. This is V hertz. Current flowing through first branch is I1. So this is I1. This is I2. And impedances are represented as this is Z1. This is Z2. Alright. Now let me solve how do we calculate by impedance technique. Okay. So for a given for this given parallel AC circuit, for this given parallel AC circuit, we will write 1 upon Z equivalent. What is Z equivalent given by? Z1 plus Z2. These two are connected in parallel, right? So it is as good as like this. So this is, let's say, Z1 and this is Z2. So what will be the equivalent of it? What will be the equivalent? Z equivalent will be Z1 parallel to Z2. Correct? These like two resistors are in parallel, right? How do we write it as R1 parallel to R2? So here two impedances are in parallel, Z1 and Z2. So we write equivalent as Z1 bar parallel to Z2 bar, and that we can write it as 1 upon Z equivalent is equal to 1 upon Z1 plus 1 upon Z2. Did you all understand this concept? This is very important. Impedances can be in parallel and we can write it in this form. Yes or no? Understood this? Hello. Okay. Now 1 upon Z is what? Y. Admittance. So Y equivalent will be given by 1 upon Z1 will be Y1 bar plus Y2 bar. So this is how we can write it in terms of net admittance. So what is Y equivalent? Admittance of the circuit. This is by admittance method. So this is Y equivalent is admittance of the circuit, parallel AC circuit. So please write it down. Completed? Now, next is how do we write line current? What do you mean by line current? It's basically I, total I. How do we write V as I bar into Z equivalent, right? So what will be I given by V divided by Z equivalent bar. And what is 1 upon Z equivalent? Y bar. So I is V into Y equivalent. Because 1 upon Z equivalent is Y, admittance of the circuit. So please note it down, the line current. I hope you are noting it down. Okay. Let me know if the pace is fine. If I'm too fast, please let me know. I'll reduce down the pace. If it is okay, I'll continue the same. Fine with this? Now what is Z1? Z1 is R1 minus JXE1 and Z2 is R2 plus JXL1. Okay, so we write down now next impedances. So Z1 is given by R1 minus JXE1 ohms and Z2 is written as R2 plus JXL1 ohms. Okay, so similarly what we will write equivalent Y1 as for Z1 G1 plus J B C1, okay, mo, and Y2 as Y2. How do we write it as? Wherever there is a plus, here it will come minus. So G2 minus JBL1 mo. Did you understand this? How do you have written this one? Y1 and Y2. Okay. Yes or no? Now, can you tell me what will be G1 from here? What will be G1? R1 upon R1 square plus XE1 square. Correct? And what will be G2 over here? G2 will be R2 upon R2 square plus XL1 square. We have seen that before, right? Conversion. Now, what will be BC1? BC1 will be XE upon R1 square plus XE1 square, or you can call it XE1 also. And your BL1 will be XL1 divided by R2 square plus XL1 square. Got it? What do you call BC1 as? BC1 is called as capacitive susceptance and BL1 is inductive. Just like we have reactance, we have susceptance. Okay, so please note it down. Did you all understand this? We have started the concept by today's lecture by discussing what is admittance, and we have written Z and Y, and we have seen that what is G1 and what is BC1. On a B, we have written B. Okay, is this clear? Okay. Now, how do we represent this with a triangle? I mean, we can call it as an admittance triangle, but will be represented like this. So this is Y, this is BC, and this is G, and this is phi 1. Okay, we can call it BC1 or G1. So will be Y1. Okay. Similarly, this will be for this diagram. It will be like this. This will be phi 2. This is G2. This is BL1, and this will be Y2. Okay. So these are the diagrams which are coming from this discussion. We'll be discussing about it, no problem at all. Now next concept is admittance triangle. So let us write it down. Admittance triangle. Like we have impedance triangle now, we have admittance triangle also. So for an inductive circuit, what was the impedance triangle given by? Impedance triangle was like this. You remember? It was given by Z, XL and R. I hope you have not forgotten. This is the impedance triangle for an inductive circuit. You can go back and check. This will be the impedance triangle. Now what was Z given by? Z square was given by R square plus XL square. Agree? Similarly, we have admittance triangle. So admittance triangle will be reverse like this. This is my admittance triangle. This is phi. this will be BL, this will be Y, and this will be G. This is called as admittance triangle. So please draw the admittance triangle. It will be exactly reverse of impedance triangle. Admittance triangle for a inductive circuit. Okay. Now how do we write over here? Here we can write it as, what do we write? Y square is equal to G square plus BL square. Okay. Yes or no? Okay. Okay. So what is G? Can I say G can be written as Y into cos phi? Yes or no? What is Y given by? Y is 1 upon Z, correct? And what is cos phi from this diagram? What is cos phi from this diagram also? It is basically R upon Z. So let me write cos phi as R upon Z. Y is 1 upon Z. I am writing in this form. So G is R upon Z square. That will be R upon R square plus XL square. Okay. So G I have written in this form. Similarly, over here in this diagram, what is BL? BL can be written as Y sin phi. Y sin phi. What is Y? 1 upon Z. What is sin phi from this diagram? XL upon Z. Okay. So here I will write it as BL as XL upon Z square, that is XL upon R square plus XL square. Got it? So we have written the formula for G and BL. Is this clear to you? Yes? We have written it from admittance triangle and impedance triangle together. If we know the admittance triangle parameters, we can easily find the if we know the impedance triangle parameters, we can easily find the admittance triangle parameters also. Y, G and BL. Any doubts over here before I proceed? This was for inductive circuit. Now we will discuss for a capacitive circuit. Is this clear to you? Yes, no? So please, yeah, hello. Okay. Now next we start with for a capacitive circuit. So this was for inductive circuit. Now for a capacitive circuit, what was the impedance triangle? Impedance triangle was like this. This was phi, this was Z, XC and R. Okay. Z square was given by R square plus XC square. So this was my R impedance triangle, right? So please draw it. Impedance triangle. Now admittance triangle will be exactly reverse. It will be opposite. So this is my admittance triangle. This angle is phi. This is uh, Y. This will be BC and this will be G. So this is my admittance triangle. Now, first case, what is G given by? G is nothing but Y cos phi. Okay, and what is BC given by? Y sin phi. Now, what is Y? 1 upon Z. And what is cos phi from here? Cos phi is R upon Z. So this will be cos phi will be R upon Z. So this will be R upon Z square, which will be R upon R square plus XC square. And the unit is mho. Similarly, Y is 1 upon Z. Sin phi, if you check over here, it will be XC upon Z from the algebra, from the geometry of the circuit. So it will be XC upon Z. That will be XC upon Z square. That will be XC upon R square plus XC square. Alright, so we have found the value of, and what will be Y given by? Y square will be BC square plus G square. So this is the way, if we know the impedance triangle parameters, we can easily find the admittance triangle parameter G, BC and Y. Understood? So this is the way we can solve it by admittance, method. Solve any parallel AC circuit using admittance method, phasor algebra and phasor diagram. Is this clear to you? Yes or no? Okay, great. Now we'll solve two numericals and we'll end the lecture. So let's start with numerical number one. Numerical number one. So please write down the statement. Calculate the admittance and draw the admittance triangle for the circuit shown below. Admittance triangle for the circuit shown below. Okay, this is my circuit. I have R and I have L. We are just learning admittance method. V is it's not given. It's only given 50 hertz. R value is given. L value is given. Let me write it down. R value is 8.66 ohms. L value is 5 ohms. So this much information is given. We need to find the circuit admittance. I hope you have noted down the numerical. So can we start with the solution? So for the first step, we'll calculate circuit impedance. Circuit impedance Z bar will be given by, here it is a RL series network, so R plus JXL. Okay, so Z bar will be given by R is how much? 8.66, and how much is L plus J? Actually, this is not L. This is actually XL value. This is XL value. L value is normally given in Henry. So XL value is given directly as 5. Okay. Understood? It's not the value of L, it's value of XL actually. So now this is in rectangular form. We need to convert into polar form. So how do we do it? In your calculators, what you will press? Shift polar 8.66 comma 5. So let me know the value of Z bar in polar form. You have your calculators with you, so let me know this value of Z bar. I'm waiting for your answer. How much is the magnitude and how much is the angle? That is 10 and this will be 30. Okay, so 10 angle 30 degree will be Z bar, right? Correct. Now we'll calculate circuit admittance. So circuit admittance is what? Y bar is 1 upon Z bar. That will be 1 upon 10 angle 30 degree. Correct? So Y bar will be, here if you multiply 1 divided by 10 will be 0.1 and this angle will become minus 30 degree. Yes or no? Now this is in polar form. This is actually polar form of Y bar. And what is Y bar in polar form given by? Y angle 5 degree more. Okay, where what is Y? Sorry, this is Y. This Y is zero point 0.1 more. Admittance is around 0.1 more. And what is phi? Phi value is 30 degrees, minus 30 degrees. So now, can you convert this into rectangular form? Please convert it into rectangular form, this one. So rectangular form, you will press shift rectangular 0.1 comma minus 30. So let me know the answer. Yeah, yeah, we write it in terms of J. Yeah, this is the in polar in the rectangular form. So this value is rectangular form of y bar admittance. And what is rectangular form given by G minus J BL for a inductive circuit, right? So what is G from here? G is 0.0866 mho, and what is BL? 0.05 mho. Understanding? Yes. Why we are calculating B, G and Y? Because we want to plot admittance triangle. Now how will be the admittance triangle? Just now we have seen it for inductive circuit. Let me draw the third case. Admittance triangle, opposite of impedance triangle. So admittance triangle for an inductive circuit will be like this. Okay, where this is Y, this is G and this is BL. What is Y? zero point 0.1 mho. What is G? 0.0866 mho. And how much is BL? 0.05 mho. Got it? This is my admittance triangle and this angle is minus 30. Correct? So this is how I complete the numerical using admittance method. This is my phase angle phi. Please note it down. Is this clear to you? Any doubts over here? Hello? No doubts, right? Okay. Now let us solve another numerical. So I hope this is completed. So we write over here. Next is numerical number 2 in next page. This is for your reference when you refer the handout. So let's write down the statement for numerical number 2. Okay. So write down a resistance of 20 ohm. Yeah. Sorry. Not necessary. See, we can write in that form provided we draw the admittance triangle, draw the impedance triangle again, and then you're telling na in this fashion, na? Yeah, numerical only, na? What is your doubt? This one? Here I'm only writing the magnitude. That's it. Understood? I'm only writing the magnitude, not the entire thing. Okay? Huh. So write down the numerical number 2. A resistance of 20 ohm and a pure coil of inductance 31.8 millihenry are connected in parallel across 230 volt 50 hertz supply. Okay, calculate first line current, second power factor, and third power consumed by the circuit. Okay, a resistance of 20 ohm and a pure coil of inductance 31.8 Henry are connected in parallel. That means how will I draw my circuit? I have a resistor R in parallel with a inductance L. Okay, so I have a RL parallel circuit. They're connected in this fashion. This is 230 volt, 50 hertz. Correct? Let me show the current over here in each branch as I1 and I2. This is I and this is also I. You remember we represented this as, this is actually R1 actually. R, this is 20 ohms and this is L, 31.8 millihenry. You remember in a parallel network we represent this by Z1 and this as Z2, correct? Yes or no? Not in terms of resistance or anything else. We represent in terms of Z1 and Z2. Okay, so this is the scenario and we have to find the line current, means this I value, then the power factor, phi is the phase angle between this voltage V and this I, so cos phi we will find, and then the power. Okay, so there are three techniques we can solve this: by phasor diagram, by phasor algebra, or by admittance method. So we'll prefer to solve it by another technique called as phasor algebra. So have you completed the numerical? Can we start solving? Yeah, everyone? Tell me yes or no so that I can start. Okay. So the first step, we represent V. You remember what was the phasor technique? Technique number 2, phasor algebra. Represent voltage, current and impedances in rectangular and polar form. Okay, so we represent it in this form and we'll directly calculate all the other parameters. Okay, so let us come over here. How is V represented by voltage? 230 angle 0. Okay, this is the polar form directly. Now, tell me what is Z1. Now, this will be very tricky. Tell me what is Z1. Anyone? In rectangular form. Tell me what is Z1. If you can tell me this correctly, that means you have understood this. There is only resistor of 20 ohms. So how do we represent it? What is Z bar ka representation? R plus minus JX, right? Here, any capacitive reactance or inductive reactance is absent. So how will you write it as? Plus minus nahi, 20 plus 0J. So this in polar form will be 20 angle 0 directly. Okay. Now similarly, what is XL? XL is not done. Huh? This is in, sorry. Arey L ही नहीं है. There is no L. You are not recognizing. This is Z1. See, this is Z1 alone, and this is Z2. Okay, so that is different. So it will be 20 plus J0. Now, similarly, you only tell me what will be Z2. So Z2 is also R plus minus JX. Tell me. No, why 20? Because R is not present, so it will be 0 plus JXL. That will be how much is XL now? XL you need to calculate. So XL is how much? 2 pi FL, right? So it will be 50 hertz, so 100 pi into 31.8 millihenry. So please calculate this number XL. Is it coming out to be 10 ohms? Check it out please. 100 pi into 31.8 millihenry. Is it 10 ohms? Please tell me. Just cross check this number. 100 pi into 31.8 into 10 raised to minus 3. How much it is? Yeah. So this will be 0 plus J10. Are you understanding? Yes or no? Now convert this into polar form. It will be 10 angle 90. You can check it out. समझ रहे हैं how we have written this? Because second case में there is no resistance. There is only inductive reactance. So it will be 0 plus J10. If you have understood this, then you have understood what is impedances properly. Completed? Yes or no? Is it coming 10 angle 90? Okay. Next, we will calculate branch current, I1 bar. So what is I1 bar? V bar upon Z1 bar. Now we can only divide if they are in polar. So 230 angle 0 divided by 20 angle 0. So how much is this? 11.5 angle 0 degrees. Correct? Please check it. Yes or no? 230 divided by 20 is 11.5. Is it? Please cross check the answers. Now convert this polar into rectangular again. It will be 11.5 plus J0 amperes. Okay. Next thing is we'll calculate I2 bar, which will be V bar upon Z2 bar. V bar is 230 angle 0 and Z2 is 10 angle 90 degree. So this will be simply 23 angle minus 90 degree. Okay. Convert this into rectangular form. It will be 0 minus 23J amperes. Okay. Why I'm converting into rectangular, you will let you know now. So I bar will be resultant sum of I1 plus I2. Now you can add two phasors by in rectangular form only. So I1 is what? 11.5 J0 and I2 is how much? 0 minus 23J. So add them together. What do we get? 11.5 minus 23J. Yes or no? Now calculate this in, this is rectangular form, right? Calculate it in polar form. So I in polar form will be, can you tell me this polar form? Shift polar 11.5 comma minus 23. How much is the answer? Yeah, correct. That is correct. Now, you know why we require this phi? I mean, this is phi, right? So now tell me what will be power factor? This is phi, right? Angle phi. So cos phi will be what? Cos of minus 63.43. Yes or no? So how much it is? Can you tell me cos of minus 63.43? 0. Yes, correct. Now it's very easy. Power consumed. Vi cos phi. Now what is the RMS value of V? 230. What is the RMS value of current? This much. 25.71. And what is cos phi? 0.447. So calculate this power. Is it 2643.24 watts? Please confirm this answer. Okay. So these are your answers. That's it. Using phasor algebra, it's very easy. Okay. Are you understanding how we are solving these numericals? Easy it is. It's not at all. It's not at all hard. It's very easy. Yes or no? Okay. Now let's say I want to plot the phasor diagram for this network. But it's not asked, but I want to calculate the phasor diagram. So how will I do it? Let me draw the circuit over here again. I mean, we will be doing it in next class, but still, I want to take it right now because we have solved one numerical on it. So we have RL, na it is. Is it L or C in this numerical? So this is the network. And I want to plot the phasor diagram. How will I plot it? Let's say the current flowing in this network is IR. And current flowing over here is IL. Total current is I. Now, how do we, voltage across V and L is same, right? So what do we do is we take voltage as a reference. Okay, I told you this, right? We take voltage as a reference. Okay, I want to draw a black line. Okay, let me save the document first. Yeah, so I'll draw the reference as V. Now I want to plot what I want to plot: IR, IL, and I. How will I plot it? Tell me. It's a pure resistor and pure inductor. It's very simple. So if you understand this properly, then you have understood how to draw a phasor diagram. Tell me, where will I draw IR? For a resistor, is it in phase with the voltage? Tell me. Yes or no? Current is in phase with the voltage or no? Hello. For a resistor, is current and voltage are in phase? Answer that much. Yeah, they are in phase with each other. So this is IR. What about inductor? Inductive current lags behind, right, by 90 degree if it is a pure inductor. So this is IL. Now where will I draw I? Total I. The resultant sum, right? So I'll take this dotted line. I take this dotted line where they are meeting. This is my I. Are you understanding? Yes or no? And what is my phase angle between V and I? This is my phase angle between V and I. So this is the phasor diagram. This I'm supposed to cover next lecture, but still, a phasor diagram for RL parallel circuit. Okay, so please note it down. It's very simple to draw actually. And the power factor is lagging. Here the power factor is cos phi, and here we call it as lagging because we have an inductor. The nature of the circuit is inductive. Okay, completed this much? Yes or no? Hello. Okay, okay, note it down. Okay, now I'll teach you the concept of RL, how to draw a phasor diagram for a RL parallel circuit and for a RLC parallel circuit, and then I'll end the lecture, and then remaining two numericals I'll solve it next time. Okay, so for this phasor diagram, RL parallel circuit, there are a few more points which I want to add. Now over here we can we write, please write it down. I bar, wait a minute, let me connect my pen tablet again. Let me close this document and open it again once more. Okay, so I bar, I can add it as IR. Here it is, IR plus IL, right? Yes or no? Can you tell me what is the impedance of the circuit? These two in parallel, right? So it will be, what is 1 upon Z? Z equivalent. Can you tell me? So if I treat this as Z, oh sorry, if I treat this as Z1 and this as Z2, what is Z equivalent? Z1 parallel to Z2, right? Yes or no? So what is 1 upon Z equivalent? 1 upon Z1 plus 1 upon Z2, correct? So what is 1 upon Z equivalent? 1 upon Z equivalent is 1 upon Z equivalent. What is Z1 given by? In the circuit, R, just R. And what is Z2 given by? JXL, right? 1 upon JXL. So I write it in terms of admittance. Y is equal to YR minus JYL. Okay, so I write it as Y bar is equal to 1 upon R minus J 1 upon XL. I write it in this form. You know where I am heading over here, correct? I can write it in terms of G, and here I can write it in terms of G minus JBL. So where G is what? 1 upon R, and what is BL? 1 upon XL. Are you understanding? Yes or no? So this is my admittance for a parallel RL circuit. So we have seen the phasor diagram also, and we have seen these equations. So this is for parallel RL AC circuit. Okay. Now can we move on to the parallel RC series, RC parallel circuit now? Yes, everyone. So we'll draw the RC parallel circuit. Okay. So take a resistor and take a capacitor, connect them in parallel. Okay, this is R, this is C. So the current flowing through R is IR, current flowing through capacitor is IC, and this is my total current. This is my voltage V, and unit is Hertz. Now tell me what will be I given by? I bar will be IR plus IC bar. Yes, I hope you're writing along. This is Z1, this is Z2. So tell me what is Z1? R plus J0, right? And what is Z2? 0 plus JXC. Yes or no? So now Z equivalent will be Z1 parallel to Z2. So what will be 1 upon Z equivalent? 1 upon Z1 plus 1 upon Z2. Okay, what is 1 upon Z equivalent? Y equivalent. And 1 upon Z1 is 1 upon R, and 1 upon Z2 is 1 upon JXC. Alright? Yes or no? Hello? This is minus actually, because capacitive it is minus, so this will be minus. Yes, so we can write it as Y equivalent is G plus, here it is JXC, sorry, G plus JBC, where what will be G? 1 upon R, and what will be BC? 1 upon XC. Are you following? Yes? Hello? Here what will be power factor? The nature of the circuit is capacitive. The power factor will be leading. Okay. Now we have to draw the phasor diagram taking voltage as a reference. So how will you draw the phasor diagram? IR and IC is there. So let's take voltage as a reference. Okay, let me draw it a little up. So this is voltage as a reference. I want to draw the circuit. IC is there. IR is there. There is total current I and V. So these quantities I have to plot on the phasor diagram. So we have already plotted as a reference. So I have taken here, right over here, taken V voltage as reference. Now, in case of a pure resistor, IR will be in phase with V, right? Yes or no? Will IR will be in phase with V, voltage V, in case of an resistor? Correct, right? So IR will be in phase with V. So this is IR. What about capacitor? Okay, in a capacitor, current is leading the voltage or lagging the voltage? Come on, by 90 degree. Tell me. In a capacitor, current is leading the voltage, so this will be IC. What will be the resultant? Resultant, you take this dotted line and take this dotted line and mark the resultant current as, let me take another color, this is I. Okay, and what is my phase angle between V and I? This is phi. Alright, so this is my phasor diagram for, so this is my phasor diagram. Understood how we have drawn this, or you have any doubts? So this is phasor diagram for parallel RC circuit, AC circuit. Okay, understood this? Yes or no? Okay, have you noted down, or shall I wait for a few seconds? Completed? Now after this we'll have a last topic for the day, that is RLC parallel circuit phasor diagrams. That's it. Okay, so let's draw a parallel RLC circuit. Okay, and we are attempting to draw the phasor diagram for it. So a parallel RLC will have R, L and C, all of them connected in parallel. Okay, and which will have a power supply, the AC supply, voltage V, hertz. Now current over here splits into three parts. This is I, so this is R, L and C. So this will be IR representing current flowing through resistor, IL representing current flowing through inductor, and IC representing current flowing through capacitor. So this is my current I. So if I want to express this I in terms of phasor, it will be vector sum of IR plus IL plus IC. Understood? Now, you remember in RLC series circuit, we have represented if the reactance XL is greater than XC, or XC is greater than XL. Did you remember? Yes or no? So similarly over here, we will consider which current is dominant among IL and IC. So we'll draw the phasor diagram for IC greater than IL. Okay, IC greater than IL. Okay, so listen very carefully. Are you all along with me? You have reached up till here, yes or no? We're in the last 5 minutes of the lecture. Can anyone respond? Okay, now don't draw. Listen first and then you can complete the diagram. Now take voltage as a reference. So I have taken voltage as a reference. Very calmly draw. And then I will be drawing the phasor diagram. Now IR is in phase with the voltage. So first quantity I'll draw is IR. Okay, this is my IR. Let's say. Okay. Then where will I draw IC and IL? Now IC is greater than IL. So it is a pure inductor. So for a pure inductor, what is my current is leading or lagging? It's lagging behind. So I'll draw it down. This is IL. Okay. Now where will I draw IC? IC is current in a capacitor is leading the voltage by 90 degrees. So where will my IC go? Leading the voltage. So here it is. Leading the voltage. Here it will be current IC. And what have we said? IC is slightly greater than IL. Here it is. IC component magnitude is slightly greater than IL. So what is IC minus IL? Where is IC minus IL? Can you tell me? Hello? This is this quantity over here. This is IC minus IL. This small one. Okay? This will be IC minus IL. The difference between IC and IL is IC minus IL. Alright? And this I will take it as a reference. And this I'll take it as a dotted line. And when I join them together, I'll get current I. So this is my current I. Let me draw it again properly. Okay, this is my current I. Did you understand? This is I and this is my phase phi. And this will be the phasor diagram for IC greater than IL, or we can say the circuit is capacitive. So your cos phi will be, your power factor will be cos phi, and that will be leading. Did you understand how do we draw it? IC, IL, IC minus IL, and then I've drawn the equivalent vector I. Understood this? Okay, great. Now finally, the phasor diagram where IL is greater than IC. So please complete this. I'll give you all 20 seconds to do that. Please draw the phasor diagrams for all the circuits properly. First we have started with phasor diagram for a pure resistor, then phasor diagram for a pure inductor, current versus voltage phasor diagram, then for a pure capacitor, then series RC circuit, series RL circuit, RLC series circuit, and now today we have done the phasor diagram for RL parallel circuit, RC parallel circuit, and now we are doing it for RLC parallel circuit. Alright, completed the phasor diagram. Can I move on now? For the yeah, okay. So next we will draw the phasor diagram for IL greater than IC. Okay, great. Now I'll take the next case, phasor diagram where the circuit is inductive, that is IL is greater than IC. Okay, so again I take V as a reference. Now I know where IC will come. IC will be leading the voltage, right? So here is my IC. IL will be lagging the voltage by 90. So I'll draw IL, and IL is greater. So I'll draw a bigger IL. Okay, where is IR coming? IR is in series, right? So this is my IR. Alright. Now where is IC minus IL? IL minus IC. Why IL minus IC? Because IL is greater. So this portion is IL minus IC. Correct? And now I'll draw the equivalent dotted line. And I'll draw the equivalent over here. So this is my I. And this is my phase angle phi. Understood? How we have drawn this phasor diagram on the similar manner. So this is here the power factor will be lagging because it is an inductive circuit. So this is inductive in nature. The earlier one was capacitive in nature. So please draw the diagram. This is my phasor diagram for a parallel RLC series circuit where IL is greater than IC. And with this we end today's lecture. So kindly note it down. And we have completed today's topic. What is left out from module number 2.3 is we'll solve two numericals more and we'll discuss about power factor improvement. With that, we'll complete the topic of 2.3, module number 2.3, and hence your ISA syllabus. Alright? So we are one lecture away to complete your module number 2.3, that is AC circuits. Have you completed?